Not understanding the difference between the number of ADC bits and the effective number of bits can cause you to get into a load of trouble by not getting the accuracy and measurement quality that you expect and need. Hi, and welcome to our new video series, Exposing Signal Integrity Myths. I'm Erin, and in this new series, we'll explore the key elements of signal integrity and how you can use that knowledge to make the best measurements possible. The number of ADC bits in a scope is one of the most talked about specifications. Because of this, many engineers tend to rely on this as the sole spec that determines an oscilloscope's quality. But boy, will they be disappointed. The importance of ADC bits is often exaggerated, while other critical indications of signal integrity get pushed to the background. The number of ADC bits spec'd on the datasheet and the number of those bits that are actually effective in showing you your measurements on screen are very different. The specification that you should really be looking for is the system's effective number of bits, or system ENOB. If you've never heard of system ENOB before, I'm not too surprised. The spec isn't talked about much, but I just said that it's the most important spec in determining measurement quality. In fact, it's what IEEE uses to measure an oscilloscope signal integrity. So why isn't it talked about? System ENOB usually isn't mentioned because it's typically so poor. Also notice that I keep saying system ENOB, not just ENOB, and definitely not ADC ENOB. You'll learn more about what the differences are of those soon, but before I dive more into why ENOB and ADC bits are so different, let's take a step back and think about why we even care about the number of bits to begin with. The number of bits is important because of quantization levels, or Q levels. The more bits there are, the more Q levels there can be. The more Q levels there are, the higher the accuracy, because we're able to capture and display more of the true signal you're working with if there are more levels. So when the ADC converts a signal from analog to digital, it can only convert at certain levels. You can imagine Q levels as each step in this animation you're seeing. Say we have a 10-bit ADC like the S series. With this, we can have 1024 Q levels. If we look at a 1.8 volt peak-to-peak signal and set our vertical scale so that we're at 2 volts full screen, with a 10-bit ADC, I should theoretically be getting a sensitivity of 1.95 millivolts per quantization level, or in other words, 1.95 millivolts of vertical resolution. However, like I said before, just because your scope is spec'd to have a 10-bit ADC does not mean that all of those bits will actually be useful in your measurements. You're lucky if you get 8 bits worth of usable quantization levels, and that's why we look at the effective number of bits. This is the number of bits that are effectively being used to show you your measurement on screen. So what is it that makes the actual effective number of bits so much lower than what the ADC is spec'd to? The number of bits is primarily impacted by noise and distortion. If the oscilloscope's random noise is larger than each quantization level, so in this case, if the noise is greater than 1.95 millivolts, then there is no way for the scope to differentiate that noise from the actual signal, therefore basically making that bit completely irrelevant. And since there's no earthly way to build an oscilloscope that doesn't have some noise, that means there's always going to be noise affecting your number of bits. And this is what drives the effective number of bits to be lower than the ADC bits available. This also means it's really important to analyze the baseline noise of an oscilloscope to be sure it's really low. Check out that video by following the link on screen or in the description. Something that I mentioned earlier was the difference between system ENOB and ADC ENOB. Since system ENOB is typically pretty low, there are some vendors that will list ADC ENOB on their datasheet. Some people see the term ENOB and take that for face value, but they're being fooled. ADC ENOB refers to the effective number of bits in the ADC and only the ADC. However, everyone knows an oscilloscope is made up of much more than an ADC. ADC ENOB is not representative of the number of bits that are actually being used in the entire oscilloscope measurement system, which is what's really going to matter when you go to make measurements. The system ENOB is the number of bits actually being used to display a signal, make measurements, and use features to analyze it. When you're evaluating various oscilloscopes based on their data sheets, be sure the ENOB is listed out based on bandwidth, and also make sure you're looking at the system ENOB rather than ADC ENOB. Don't be fooled by any impressive ADC specifications. While the number of ADC bits is still important because it means more quantization levels, that could be irrelevant if the rest of the oscilloscope isn't designed properly. Understanding ENOB and what that means to your measurements you end up making is critical in creating a design that has the accuracy you and your customers need. I also mentioned it's important to look at the noise floor of your scope to determine the overall quality. Learn more about vertical noise and some of the other important signal integrity specifications by checking out the rest of this video series. Do you have a topic you want to learn about but you can't find a video for it? Let us know in the comments. We always want to be creating new content that will actually be beneficial for you in your daily testing. Thanks for joining me today. Subscribe to our YouTube channel to stay up to date on our new content, and check us out on Facebook, Instagram, and Twitter.